This is section 7.3, which is multivariate linear systems and row operations. We're going to focus on Gaussian elimination, elementary row operations, and both row echelon and reduced row echelon form, and then how we can use matrices to solve systems. So first of all, these first couple slides are kind of explaining what we're going to get into with this section. So equivalent systems of linear equations. So we are allowed to make changes to a system of equations as long as we are doing something to the entire equation to keep it equivalent. So these are kind of the different operations that would produce equivalent systems. We can interchange two equations. We could multiply or divide one of the equations by any non-zero real number, and we could add a multiple of one equation to the other equation in the system. And you've seen this before when we've solved systems algebraically, and we're going to look at that again today. So we have row echelon form of a matrix and then reduced row echelon form of a matrix. So row echelon form, just to kind of give you an idea, is that you're going to basically, along the diagonal, you're going to have zeros in the other positions. So you could have 1, you could have some numbers here, and then maybe, so this would be row echelon form. So you can see that we have the first entry in any row with non-zero entries is a 1. So we have that here. And then you can see it's kind of, we have zeros leading up to the 1s. So it kind of forms the diagonal there. Now, reduced row echelon form is what you're going to want to be able to find out what each variable is equal to. So you're still going to have the 1s along the diagonal, but you're also going to have zeros. If I can write these all lined up here, that would help. So you're also going to have zeros here. I overshot how big I wanted my matrix to be. And then you might have, if you have an augmented matrix where you put in the solutions as well, you might have your answers over here. So, but you can see that this part right here is 1s and zeros. That's the difference between reduced row echelon form and just row echelon form. Okay, so elementary row operations, we can take a matrix and we can do elementary row operations to put it into row echelon form or reduced row echelon form. So you'll notice this list is similar to what we talked about, what we are allowed to do with a system of equations. We can interchange two rows. We can multiply all elements of a row by a non-zero real number, and then we can add a multiple of one row to another row. So you should notice connections, and as we go through the examples, probably even more connections. So we're going to solve this system of 3 equations by hand. So I like to number my equations, so that way I can refer to them without having to read out the whole equation. So when we do, so we're going to use Gaussian elimination to solve this. So you can do substitution with systems of 3 variables. I prefer to do elimination. It's a little bit more organized. So I am going to take the first 2 equations and I'm going to eliminate x. So I'm going to take -2 times equation 1 and then equation 2. So if I multiply the top equation by -2, that's going to give me -2x plus 2y minus 4z equals 6. And then we're going to keep the second one the same, 2x plus y minus z equals 0. So if I add those together, the x's will cancel, and I will get 3y minus 5z equals 6. So I'm going to call that equation 4. So now I am going to take equation 1 and 3 and add them together because they already have x values that will cancel when I add. So this is equation 1 hard to write small. Okay, there's equation 3. So those x's will cancel. I'll have y minus z equals 4. And that I'm going to call equation 5. So now by eliminating the x's and creating 2 new equations, we have 2 equations now with 2 variables. So I'm going to take equation 4, I'm just going to leave equation 4 right there, and do negative 3 times equation 5. So I'm going to keep equation 4 the same, and then that would turn into negative 3y plus 3z equals negative 12. So then the y's will cancel, and I will get negative 2z equals negative 6, which then if I divide by negative 2, I get that z is 3. So then we're going to take that and back substitute. So I'm going to put the z into equation 4. So that'd be 3y minus 5 times 3 equals 6. So that'd be 3y minus 15 equals 6. Then we're going to add add 15 to both sides. So I get 21, divide by 3, so y is 7. Then I'm going to plug both z and y into equation 1. So that would be x minus 7 plus 2 times 3 equals negative 3. So then I get, so that would be x minus 7 plus 6, so it'd be x minus 1 equals negative 3, and I can add 1 to both sides, I get negative 2. So that means my solution would be negative 2, 7, 3. So what we're going to do is we're going to look at this problem now in multiple different ways of how we can solve this. So this is one way. One way is that I can solve it by hand. This is a long process, but it's helpful to understand how to do it by hand, so that way if you're using technology, you can kind of understand if your answer is reasonable or not. Okay, so the next thing we're going to look at is what this looks like if you're doing elementary row operations. So what I took a picture of here, this is the exact same process that I just went through on the previous slide, except you can see that we're doing it with a matrix instead of an equation. So these are the same 3 equations that we started with, and you can put them into an augmented matrix. So an augmented matrix means that you're including, you have all the coefficients, and then you also have each equation is equal to, and that then we are going through the same process that we did on the previous slide. So you can see the first step was to take negative 2 times row 1 plus row 2, and then you're replacing row 2. Then you're taking row 1 plus row 3. So that should be very similar to if you think, okay, I took equation 1 times equation 1 plus equation 3, and I got my new equation. So what I did algebraically is the same. We can do the same process using these elementary row operations. I'm also going to show you how to, let's see if this slide, yep, we're going to sidestep here for a second. I want to show you how to do this on the calculator. So this is, you can see how much work goes into this. And so we have the benefit of technology. So I'm going to show you, if we go to, this is our matrix calculator. So I can input my original matrix. So I'm going to do a new matrix. I'm going to make it 3 rows and 4 columns. So, and I'm going to put the coefficients. So it'd be 1. Negative 1, 2, negative 3, and then 2, 1, negative 1. So these are the coefficients from my equations, or from the matrix if we're looking at the row reduced example. Negative 3 and 7. Okay, so that is my matrix, and then I'm going to find the row reduced. So you can see our options here. You see the RREF, that stands for reduced row echelon form. So I'm going to do reduced row echelon form of matrix A, and you can see without even hitting enter, it gives me my values. And you'll notice that X is -2, the first line, Y is 7, the second line, and Z is 3 on the third line. So reduced echelon form of an augmented matrix, you can use Desmos. The other thing you can use is your graphing calculator. So just to remind you how you're going to do this, you're going to go second, and then you see the word matrix above the X to the -1 right here. So I don't know why that won't, I don't want it to say here. There we go. Okay, so second, X to the -1. So I'm going to edit matrix A. So I'm going to enter, it's going to be a 3 by 4 matrix. And I'm going to put my same numbers in, 1, -1, 2, -3, 2, 1, -1, 0, and -1, 2, -3, 7. Okay, so then I'm going to hit second mode to quit, get me back to the main screen, and I'm going to go back to my matrix menu, and I'm going to go over to math, and then if we arrow down all the way to B, you see the RREF. So I'm going to do that, hit second, X to the -1. I'm going to tell it I want to find the reduced row echelon form of matrix A, and look, I get the same answer. So I'm showing you how to do this multiple ways depending on the technology that you're using. Okay, so back to our examples. So the last thing that we're going to talk about is how you can use the inverse of a matrix to also solve a system. So the invertible square linear system. So if we have a matrix, if we have a system, we can write the coefficient matrix, which does not include the solution part, and we can take the inverse of that times and multiply it by the solutions, and that will give us our variables. So I'm going to show you, this is one that an example might make more sense than me talking about it. Okay, so solving a system using inverse matrices. So what we're thinking about here is that, so we have matrix A times our variables equals matrix B. So if we want to solve for X using matrix operations, we would take the inverse of A times B. So what that's going to look like, so first of all, I'm going to make a matrix A right here that is just the coefficients. So it's 2, -3, 2, -2. Then I'm going to make a matrix X that is my variables, X and Y. And that is equal to matrix B, which is 0, 10. So what I'm going to do is I'm going to take the inverse of matrix A times matrix B, and that's going to give me X. I probably didn't need to write that again. Okay, so let's go to one of our technologies here. So I'm going to go just to our Desmos. So I'm just going to delete that. Didn't mean to zoom in. Okay. So, how do I zoom out? Ah, fun technology. Okay, so we are going to do a new matrix. Actually, I want to clear everything. Clear all. There we go. Okay, so I want to make my matrix, new matrix. We're going to make it a 2 by 2. So I'm going to put in 2, -3, 2, -3, 2, -2. So that's going to be my matrix A. Then I'm going to do a new matrix, and it's going to be 2 rows and 1 column. And this is where I'm going to put 0, 10. Okay, and now I'm going to do, so you can see we have the options here. I'm going to do the inverse, the inverse of, if I can get this here. Okay, having lots of issues. Okay, let's try this again. We're going to do A, type the inverse, times B. And there we can see we get 15, 10, which means that our x is 15 and our y value is 10. In some ways you might be able to do, since this is a 2-variable equation, you might be able to do it by hand faster than typing in all the matrices. So if we go back to here, that tells us we got that x was equal to 15, 10. So that means the solution x is 15, y is 10. So that's how we can use inverses to solve as well.